make sure they're not super loud so I don't blow any headphones out.
I couldn't tell from your thumbnail, Andrew, and I thought for a minute he actually were on a bus right now.
Oh, yeah, I think that's the T. A really, really old picture.
I'm sorry, I just realized I had headphones in, so I couldn't actually hear anything that anyone was saying there.
Yeah, sorry. I said I'm gonna, do you mind if I test if this audio goes through? It should, last time I checked, on sharing my computer, the presentation.
Cool.
All right. So if I present this, I apologize if this is loud, but let me know if you can actually hear this or not.
Okay.
I might be told that if I had wished to follow the rules of pure morality.
Sweet. Thumbs up?
Yeah. Yep.
And it wasn't obscenely loud or anything?
No, it's good. It's good volume. It's about the same volume as your voice.
Great. All right. Then I'm good to go. I'm going to set this.
Cool. And John, do you just want to give a quick go at presenting? Let me see. Go ahead and admit everyone.
Can you hear me now?
Yes.
Okay, great.
Cool. And let me just so GU or ZU, are you going to be the person in your team who has the slideshow up? Xiang, I'm gonna go ahead and make you a co-host as well. There you go. All right. So, are there any questions before as we sort of get close to starting today?
Should we save time to field questions at the end?
Yeah, I think so. So I sent everyone, a couple of other folks' papers. I tried to kind of match things up based on content on some level. So yeah, if you could sort of save maybe 3 or 4 minutes for questions, that would be great. We have some splash time at the end of the whole thing as well. So. Yeah, it's been it's a good group of projects this year. There's been I think this will be it's fun group of presentations, and it's really fun to actually get to read through them all. So I think that this will be interesting for everyone because a lot of them are very, very different. There really is quite a diversity of what can be done with machine learning here. It's huge. There's a huge storm blowing up outside.
Wow, it's raining outside.
Yeah, I'm actually. Can you guys hear that over my mic?
Not really.
Yeah, it's hailing.
Oh my. I retreated to Pennsylvania, and it's a little cloudy, but it was raining earlier, so hopefully no bad storms come later.
Not too bad. Where in Pennsylvania?
Near Lake Wallenpaupack. Nice and isolated in some woods over here.
Yeah, I lived in Lancaster County for a while when I was younger. Sort of off in the farmland with the Amish. All right. So yeah, I'm closing out the end of the semester as well. There's one topic that oh yeah, so I want to say everyone's grades at this point should be on Blackboard, and things should be graded out. So if you turn something in and your grade does not reflect that on Blackboard, please let me know as soon as possible. I'll be waiting until after the presentations to put the final grades in, but it's going to happen soon, so get everything squared away. And a couple of people have expressed the desire to either continue working on their project or continue putting through edits and whatnot. And if you are interested in doing that, so again, I'm going to try to create over the next couple of maybe week or two some sort of nicely presented gallery for all of these projects. So if you have updates to your project or you have updates to your paper that you're interested in sending me, please let me know and I'll be more than happy to continue to keep that updated. Are there any questions before, are there any lingering questions from the semester? Yeah, there were a couple of topics as well that we didn't get to cover. So, I mean, as you guys are aware of, we sort of lost 2 weeks over the course of the semester. And the big one that I apologize for not getting to is hyperparameter tuning. So hyperparameter tuning, of course, is sort of what you guys all did at the very end, of, okay, so when we actually have made some decisions about what models we get, we want to look at, and we've made some decisions about how we want to tune our parameter space and do things like, look at different learning rates and look at different learning rates and look at different optimizers and all this kind of stuff. So there's a whole kind of art of doing that, which is the art of hyperparameter tuning. And there's a bunch of libraries that exist out there to help you do that as well. So if you really do want to look at, training, 100 different neural network architectures, for 10 APOCs each and recording sort of how well they do, there's some good libraries out there that can facilitate that. You kind of put in, you can also you can write them yourself. But that was kind of the one topic that I really wish that I had hit on the machine learning and engineering side. And so in this class, we have wound up, so we've done a lot of math, of course, but we've also, we've wound up doing a lot of sort of machine learning engineering, right? this class in some sense is more, at the end of the day, was more geared towards the practical, how do we actually do the machine learning. We dovetailed into the theory a bit, and then the last week and a half, we discussed at least the theory up to through learnability. But there's a lot more to say about the actual mathematical side of this and how mathematically machine learning is understood. And there's been the potential in the works to do a machine learning 2 class that really kind of explores the mathematical side of things. So it kind of basically starts where we stopped with BC dimension, and then goes farther into a bit of the theory of optimization of complexity, a bit of the theory of high dimensional statistics, and kind of tries to make very precise some of these theories. So if anyone is interested in taking such a class, and if there is enough interest, then we could look into running such a thing in the fall. There is also a class that is being developed, hopefully for next spring, that's on topological data analysis. So that is kind of topological methods in usually unsupervised learning. And that'll be more of a PhD level class probably, because there's some interest in developing the PhD program a little bit more towards aligning with the Northeastern 2025 goals about artificial intelligence, machine learning, and whatnot, and bringing some of that into the pure math departments. So pure math department is very, very, it's very algebraic geometry focused at the moment. So if you're interested in, that is another place where if you continue to be interested in machine learning, like on the more theoretical level, I would keep an eye out for that class. Any other? So basically the machine learning announcements. Oh, if you want to, I think there was one of the groups that did the work on the Boston 311 app. So they'll be presenting tomorrow. But they pointed out actually that the Boston 311 data, which is publicly available online, is also tracking all the reported cases of COVID-19 currently. So that's one of the main places where people are reporting having symptoms and reporting infections themselves. So if you have any interest in doing some hands-on epidemiology in machine learning, that's a data set that's open and available. I encourage you to take a look at it over the summer. All right. Are there any questions before I cede control to our first group, who's going to talk about mapping lead poisoning in Providence, Rhode Island? All right, well, I will go ahead and cede control. Let me see. All right, I should have made you guys hosts so that you can present. Let me know if that's not working for some reason.
Hello?
Hey.
Okay, so we're gonna start.
Fabulous. And I'll give you a 10-minute warning. So after 10 minutes, I'll give you a warning.
Okay. So Good evening, everyone. I'm Evan, and this is Zexian, Jiayi, and Zechen. Our group's topic is mapping leak in Providence, Rhode Island. Now let's have a short introduction. Nowadays, lead is a major problem in many post-industrial American cities. Lead can cause serious health problems if too much enters your body from drinking water or other sources. It can cause damage to the brain and kidneys. This problem also takes economic costs on hundreds of thousands of people every year in the United States. In Providence, Rhode Island, in-home lead piping is known to be a problem because elevated lead levels have been found in the sewage outflow. Also, many properties have field lead inspections. So therefore, the main object of our project is to build a model to inspect lead poisoning level by comparing the data found in Providence, Rhode Island. Our data sets are found from two government websites. Here we call them website A and website B for convenience. You can see from these two images, the website A contains raw data such as street number, street name, street type, town zip, and labels, which are characterized as the degree of lead safety, which includes in the second image, the safe for habitation, multiple poisonings, second notice of violation, and lead safe certificate. Next. The website B contains all building attributions, include detailed information such as style, grade, storage, occupancy, and land use. But here we only choose the information that we think it is useful. We don't use all the information in website B.
So I want to show you guys our data representation and the processing part. The first step is to download the website A and save it as an HTML document on our local machine. Here's an example of a piece of data from the original website. It is labeled as unsafe for habitation. The second step is to extract the house's information from the HTML document using Beautiful Soup. The Beautiful Soup is a Python package that can be used to parse HTML documents. We use it to extract the data more efficiently. And here's an example of the data that we got. The data we got from the first website include the location of each house. We go to the second website and search for the building attributes of the website using the location information. Again, we use Beautiful Soup here. One thing that I want to mention is that we found 158 lead poisoning data and 9,148 data that are not lead poisoning data. Since we are more interested in inspecting the lead poisoning level, we only randomly picked 80 safe data and put them into our training set. After this step, we use GeoPy, which is a Python client, to find the coordinates of all the houses and save all the information we found into an Excel sheet for later use. And here is what we got. Then we convert the data to a data frame. In order to put our data into the model, we encoded each attribution as an integer. For example, the style 3 family is encoded as 0, style 2 family is encoded as 1, etc.
Now come to the solving the problem part. We have tried many ways to get a better fit to our data, and the results from decision tree and random forest performed better than others. So we will focus on these two methods in our presentation. The first one is decision tree. Decision tree is a prediction model representing a mapping between object properties and object value. A decision tree contains nodes, bifurcation paths, and leaves. Each node in the tree presents an object. Each bifurcation path stands for a possible probability value, and each leaf means the value of an object along the path from the root node to the leaf node. As we have learned from class, we split the data into regions along one feature and model the response by taking the mean label in each region. By choosing a variable and splitting point, we obtain better and better fits. We use decision tree classifier in Python sklearn library to do the loop until a stopping rule is applied. And next is the second method, random forest. Random forest is a popular way to reduce high variance from decision tree. And an estimator is the number of sub-decision tree. Just to mention, in our model, we use an estimator equals 80 for better fit. Here, I want to emphasize our group use the out-of-bag score to validate the model instead of mostly choosing validation accuracy. Why we do this? When fitting the model, some of the training set data are taken out and used as validation set later. Out-of-bag score is the accuracy of predicting the taken out set. For some reasons, we cannot get enough and accurate training data. So we think using out-of-bag score is a better choice to validate.
So the validation accuracy for decision tree with max steps equals to 2 is 0.35. For max step equals to 5 is still 0.35. And for max step equals to 8 is 0.55. And the out-of-bag score for the random forest model is 0.58. And here is a picture of the decision tree with max steps equals to 2. The first line of each node is the statement used to categorize the data. If a slice of the data satisfies this statement, it is categorized as the left child node. Otherwise, it goes to the right one. So each piece of data will be categorized until it reaches a leaf node. And the samples is the size of the current node. The last line is the classification. So class equals to 0 is unsafe for habitation. Class equals to 1 is multiple poisoning. Class 2 is second notice of violation, and class 3 is safe. And this is the mapping part. The left plot is the true mapping of some of the data from the original data set, and the right plot is the mapping of the decision tree prediction. And in this slide, the right plot is the random forest prediction mapping. So for these two slides, if you compare the left plot with the right one, you can find that the accuracy is about 50%.
And now here's the conclusion part. In this project, our group acquired the data from the government websites. We tried some models to feed in the data, including decision tree, random forest, agglomeratory clustering, a bagging classifier, and AdaBoost classifier. The validation accuracy for clustering, bagging, and AdaBoost are low, so we didn't in our result. The validation accuracy in addition, the out-of-bag score of random forest is 0.58, which has the highest accuracy among our models. However, all the accuracy rates are not ideal. There are several. First, we have some problems when scraping data. For example, there were some bad addresses in the website A. These addresses did not exist anymore. Some coordinates of the house locations could not found by using GeoPy. About 1% of the data was marked as unsafe. The second is when scraping the data from second website, we only scrap the data that we think are as useful. So we might have missed some important attributes in this step. The third is we also tried one-hot coding to convert every label and got a better accuracy than encoding each label as different integers. However, we can't able to understand this result. And about our future improvements, First, one of the biggest reasons that we can't get a better model is that we don't have enough training data. In the future, we can try some different scrapping methods to increase the data sample. And second, we can also, as mentioned in the deficiency sessions, we only acquire the building attributes that we consider as useful. And for future work, we can scrap the pictures of each house and use the CNN model to detect its poisoning level. And third, we can try to present the mappings in the Rhode Island map. So Rhode Island citizens can see the lead poisoning level distribution on the map directly. Thank you. Here is our reference. And do you have any questions?
All right, thank you guys very much. I would encourage, so if people have questions, maybe type them into the chat might be the easiest way to do it. But in the meantime, I've got one question. So if you go back to where you show the decision tree. Yeah. So if you notice here, your decision tree is splitting off latitude and longitude, right? It's actually splitting off latitude twice. And so I know something that wasn't included in the presentation, that even with the larger decision tree, it always seemed to split on latitude and longitude. So it was basically pulling out this geographical data. Do you have any idea what would happen, or do you have any hypothesis about what would happen if you just dropped the latitude and the longitude and tried to do the fit?
Actually, we got a different result if we don't use latitude and longitude at all.
Okay, yeah, what kind of result do you get in that case?
It's a much lower accuracy. Since all the attributes seems the same, unless they are safe or unsafe.
Yeah,
is it like 25% lower?
Kind of.
Okay.
Yeah, but it's categorized using different attributes like occupants or grade.
Okay. You've got a question from Rubing up, if someone wants to answer
that. Since this is an categorical data, so I think if we use classifying or clustering is much better. But when we try some clustering model, we get lower accuracy than these two. So we choose this model.
So can everybody hear me?
Yeah.
So my question is, so you are choosing different method on both the training set and the validation data set, right? And you just mentioned because these two methods showing high accuracy on the validation data set, so you choose to, so you guys decide to use these two methods, right? So my question is, actually, when you're choosing different methods on the same training set and as well as the validation data set, you are actually learn from the validation data set, right? That also caused the overfitting on the validation data set. And so I'm kind of wondering why you guys don't divide another independent test site. I mean, because you are choosing different method and feed on the validation data set. So during your process, you are actually overfitting the validation data set. So I would rather be more interested in what's the performance of these two models on another independent test data set. So you guys ever tried this before?
Yeah, actually, one of the reasons is that we don't have enough data set for this model.
Okay, I see.
Yeah, we only got about like about
100.
150 data set.
No, only 100, since there are lots of bad addresses. We can't find all the building attributes.
Yeah, unfortunately, a lot of the leaded buildings got knocked down, so so they no longer appear in the database. Do you want to quickly answer Andrew's question, and then we will jump to the next group?
We don't turn in the tree since we don't know why they have a lot of latitude and longitude classification.
So
that's all.
All right, thank you guys very much, and
Thank you.
Thank you.
Stop sharing.
I'm not sure if there's like a good applause button or something on here.
Yeah.
Okay, so next we are going to hear about new loss functions in deep learning-based side channel attacks.
Yeah. Okay. Can you guys hear me?
Yep.
Yeah. Okay. Sure. Good afternoon, everyone. My name is Xiang, and my friend Ziyue and I will present new loss functions of deep learning based on side channel attack. It's a project combining cyber attack and deep learning. This is the outline. I will introduce first three-part side channel attack, AES encryption.
Quickly, we can't see your screen if you've got
yeah. you can. Oh, sorry.
It's all right.
Oh, yeah.
Okay.
Can you see my slides?
Yes.
Oh, sorry.
No worries. Sorry about that.
Yeah, I'm sorry. Yeah, I will introduce first three parts about side channel attack, AES encryption, and or power-based attack on AES. And Ziyue will introduce some deep learning attack. And yeah, in cyber attack, one of the most important part is expose, alter, disable, destroy, or steal some data from target machine. So, for example, if we want to break cryptography, and normally we can steal the key from target machine in two ways. So we can attack directly, such as brute force, or we can attack in side channel. So what is a side channel attack? Think about this example. We have a box, so how can we know what is in the box? Directly, we can break or open the box and get it. Or we can shake the box or with the box, guess what is in the box. So it's the sound or the way is called side information. So more side information we get, more accuracy guess we have. So this is about side channel. And in cyber attack, side channel can be power, heat, sound, or time. One of the most popular side channel is the cache-based side channel attack. We're also working on that. But in this project, we will focus on the power-based side channel. Yeah, this is another example about combining side channel attack and machine learning. Yeah, this is a acoustic attack on keyboard with machine learning. The leakage point is a different key on the keyboard will have different sounds. I mean, the human ear cannot identify the difference, but the machine can distinguish which key we press. So we can only collect the sounds of key on the keyboard and feed them in the neural networks. We only need a simple networks, train the model, and then evaluate our data. Some conclusion about this interesting attack is the laptop keyboards are less vulnerable than the standard PC keyboards, but telephone pads or ATM pads are very vulnerable to this attack. So actually, please be careful about it. And yeah, our target in our side channel attack is AES encryption. AES encryption is one of the most popular encryption algorithms. One AES encrypt rounds contain 4 parts. It's sub-bytes, shift rows, mixed columns, and add round key. For AES 128, it has 10 encryption rounds. 128 is the key size, which means longer key means it's harder to be compromised. So AES 192 has 12 rounds, AES 156 have 14 rounds. And yeah, this is a S-box will be used in sub-bytes part in AES encryptions. It's a lookup table, and it's a nonlinear mapping. For in the encryption part, we use icebox, and in decryption, we use inverse icebox. So this is an important part for in our attack. And the next is the power-based side channel attack. The leakage point is the chip is dynamic power consumption. So for power consumption leakage data information, it has to be data dependent. So in CMOS, whenever the output switches, the output competitance needs to be charged or discharged. The charging leads to a higher current, and which means if the element is working, it has more power consumption. So yeah, this is a leakage. And the power-based side channel attack contains two phases. Interaction phases and analyze phases. In the first phase, we just collect the power trace from the target devices and then analyze the data based on some static models. Yeah, this is a power trace we collect from of AES 128. We can see there are 11 dips. Each dip represents at round key part in each encryption in each encryption rounds. So it should be 10 rounds. One more dips comes from the last rounds. The last rounds is incomplete rounds. It has a round key, so it should be one more dips in the plot. And next, my friend Ziyu will introduce how to recover the last round key from this power trace.
Okay, guys, can you guys see my screen?
Yes.
Okay. So yeah, as Xiang just mentioned, we're in this project we're target the last round of AES 128. So let me mention a notation here. So you can see the LJ is the J's power point in the power leakage L, and we call the correct key of the we call a specific correct key of the target byte of the last round key to be the KC, which means the C means the correct, and for the other wrong key guesses we name it as KG. And here the capital C means the value of cipher, the value of the ciphertext of the target byte. So here I would mention that in the last round of AES, the round key has 16 bytes, and one attacker can follow the byte divide and conquer strategy to break the last round key byte by byte. So here we specify the situation that we only gonna recover 1 byte out of 16 bytes for the last round key. So here is the mechanism. So during the last round of AES 128, the power consumption, which is the measurement we got, contains some leaky points, which has a very strong relationship with the correct key, which I mean the leakage here would follow the function shown here, which is the Hamming weight function of the inverse of Xbox of the XOR between the correct key value as well as the ciphertext value. But the relation becomes much weaker when it's the same expression under the wrong key. So that gives us the approach to distinguish the correct key out of other wrong key guess. So here XOR is the standard XOR operation, which operates on the binary form of different integers. And the Hamming weight is a traditional model using security, cybersecurity, which is the number of ones in the binary form of any integers. For example, if we look at Hamming weight of 10, we first express 10 in a binary form is 0, 1, 0, 1, 0, and the Hamming weight model give us the result too. So let's talk about first about some traditional side channel attack method. So for example, sorry, where we go? Ooh. So for example, the CPA, which is the correlation power analysis, computes the correlation between the leakage measurement as well as the leaky label I was talking about earlier. And they compute the correlation for all the power points. Then they pick some the highest correlation through any for any power leakages, and they say, okay, the key candidates corresponding to that correlation will be the correct key. But here, as I just mentioned, the traditional way of attack only can focus on single power time points at a time. But actually, multiple power points contain the secret information. So the question is, how can we combine all these leaky points together? And how can we also deal with some side channel countermeasures? So in this project, we designed a deep learning based side channel attack, basically because the deep learning model can accept high dimensional data as the input. And some already published paper also mentioned these type of attack are also resistant to some existing countermeasures. So let's first talk about the design of our DM model. So for our DM model, we required entire measurement as the input instead of a single power point. Then for the prediction, here we just doing a multiple label multi-classes classification problem. So the output will be the prediction of the function I just mentioned before. So because in the training process, we know the true key, so we can build the label. Then in a real attack, the DM model will take in charge of predicting the label. So for the label type, we just simply choose the MLP as well as this the convolutional neural network with softmax layer, because here again it's a multi-classes classification problem. So in the training, we use both the power measurement belongs to the training set as well as the label. And in attack, we fit in the single power measurement at a time, then we can get 9 probabilities, because here the label ranges from 0 to 8. So in a real attack, we divide the whole attack into 4 steps. So first, given a attacking power set with size n, we first compute the label for each round key guesses. So you can imagine because there are 256 key guesses. So there will be 256 times capital N label will be computed. Then we feed all these N power measurements into the DM model one at a time and collect 9 times capital N probabilities. Then here's the key, how we compute the score for each key candidates. Actually, you can see the formula here.
Quickly, I have to speed you up here. You're at 15 minutes. So finish up, but yeah.
Okay, so we'll take the log transformation and add those probability together, because we assume here the probability comes from the same distribution. So if you do the log transformation and sum them up, then according to the large number theory, those kind of score will follow Gaussian distribution. So here the Gaussian entropy is the evaluation tool that's very important to us, because it is the expectation of the rank of the correct key. So the rank here, according to the formula here, the Gaussian entropy, which is important metric, can be computed using a Gaussian distribution. And that gave us a way to compute the Gaussian entropy in a differentiable way. So because here we got a differentiable quantity, we can use this as a loss function. So before, in the traditional way, when people doing the multiple classification, they actually use the negative log likelihood or cross entropy. But here, instead of using these two loss functions, we directly using the Gaussian entropy as the loss function, because this is the true quantity we try to minimize. And here is the data set. First one is a simulation one, and the second one is a real data set. We designed two corresponding DM models for these two data sets. And here is the result. First one I want to show is because the Gaussian entropy, the one we really want to minimize, has a non-monotone relationship between the negative log likelihood or the cross entropy from this plot. So that leads to a question: should we use the negative log likelihood or cross entropy for this type of a question anymore? And also the second plot also showed the same picture, but just in a different aspect. Because first one, we're monitored Gaussian entropy during the negative log likelihood training, and the other one is in the opposite way. So the last picture, the last slides, we showed our training used Gaussian entropy as a loss function, and we compared this type of a training with traditional training using negative log likelihood as a loss function. And we observe, we monitor the Gaussian entropy of the target DM model on a validation data set through the whole training process. And the result is the DM model using Gaussian entropy as a loss function give us a much better performance than using negative log likelihood as a loss function. And the last picture shows we also achieved successful attack on the real leakage data set. Thank you. That is all I want to summarize here. Sorry.
Great, thank you guys very much. Are there any quick questions? I had a kind of a quick, just high level question, because I'm not that familiar with this world of side channel attacks on power consumption. How much can you actually recover from this? Like, I mean, can you actually, like, with a 30% chance, recover a key pair, or?
I mean, here we're talking about some old version of AES encryption, because it involves many T-table lookup operation will potentially leak many information. So here right now the conclusion is, without any countermeasure, we can 100% recover.
Oh really?
Yeah.
Oh wow.
Given a adequate data set, not even that much, like a couple of like a 10,000, around 10,000, or even 100, not 100,000. Yeah, we can recover the key, but I mean, it's really some very old version of AES. So it's more like we're not specific for AES, but more general encryption algorithm involves some T-table lookup. Those kind of a leaky operation of the computer, not exactly the AES, but I mean, AES is a really great example.
Very cool. Are there any other quick questions? All right. Thank you guys very much.
Thank you.
Thank you.
Absolutely. Okay, so up next, we're going to hear about predicting the VIX stock label from headline data. And Josh, can you present? Josh.
First, I need to unmute.
Let me make you a co-host. There you go. Okay.
Screen. That one. All right. Can you see me?
Yep. So I'll put in chat when 10 minutes are up, and then yeah.
I think I just lost chat, but I do have a timer.
Okay.
All right. So yeah, I did my project on predicting the VIX ticker volatility from headline data. Oops. So we're going to go through the problem data set, how the representation or how the data was processed, the model and results. The problem in general is, whoops, I don't know what that was. Oh, somebody's trying to get in the room. Weird.
Yeah, sir. I'll let him in. Don't worry about it.
Okay. Yeah, so the goal was to utilize headline data from a couple of sources that Professor Bade had posted to tell what was going to happen the next day on the volatility index. The volatility index is a metric of just expected fluctuation in price, and it's sort of forward-looking over a 30-day period. And obviously, this is time series data, so an RNN would be the selection, and it's categorizing the data from the headlines as a sentiment analysis problem. So the data set, as I got it, was ABC News, which is oddly enough not the ABC you're probably thinking of. It's Australian something or other. And then Reddit news channel. The ABC News ran for these dates you see up here. It was by far the larger of the data sets and had 250 headlines per day. The Reddit channel was narrowed down to 25 headlines per day, and was over a shorter period. The target data, the VIX, was available at the website, and there's actually two ways this was calculated. When it was first a thing, it was based off of the S&P 100, and then they switched over to the S&P 500 a little bit later, and then went back and back calculated, and all of those are available. So they had the daily high, low, the open and close available. So in order to do the sentiment analysis, there's a Harvard, I don't know how to say this, it looks like 4.4 to me, but IV4 dictionary and a Laswell dictionary that's sort of compiled and available online. And what it does is it just takes each word, like you see in the right-hand corner there, and gives it a grade, as in positive, negative, strong, weak, active, passive, and then there's actually sub sentiments underneath all of those, but they weren't used. So what I did was just break up the complementary pairs into 1 and -1 mappings, which created a 3-dimensional vector space for each word that I could find in a headline that happened to be in the dictionaries. And so in scoring these things, there's a couple of different ways to view it. So each headline in and of itself went through, summed everything up, and then took a unit vector as to not overvalue longer headlines or ones that just happen to have more words that were in the dictionary. And then from those individuals, I either added up, I added up all of them together for each day, added them all up and took an average. And then I added them all up and did a unit vector again. And did this for each data set, as in the ABC data set, the Reddit data set, and then just adding everything together where they had dates that overlapped. So the VIX data was extraordinarily tail heavy, which led to taking a delta to try to correct the distribution. And you can see there on the right that starting from the tail heavy data, when you take the delta, it looks a lot nicer. And then down at the bottom is a representation of the three-dimensional vector for each of the data sets. And so that was the basis and the starting point for the work. From there, created 72 models from all the different combinations of parameters, or available sets, right? So we had cumulative, average, and unit vector, and then we had open, close, and then delta, so on and so forth for everything. In doing this, it was a short training session, only 50 epochs, a small batch size, and actually to even remove more variability. Once the model was created and initialized, I saved off the initial weights instead of rebuilding the model each time. Actually just reloaded the initialized random weights to make sure that that variability was removed. From this, it became pretty evident that the VIX delta close was the higher performing. So went back through and then trained deeper on all the cumulative, average, and unit vector sentiments for all the three data sets. And that's the picture up there in the right. So from there, we saw that actually the individual data sets, ABC, cumulative, and Reddit cumulative, did the best, which led to the idea to just dovetail the two together. So take ABC and put it in front of Reddit, which actually makes the data set a lot bigger and seemed to be the best performing metric or best performing feature set. It's not working. Okay. Well, so from there, I performed a series of grid searches, starting with LSTM and GRU node types, spattering of numbers of nodes, and then some different dropout rates. Trained rather shallow and held epochs, batch size, and learning rate constant. And as a result, we ended up with an optimized set, and then iterated through this until we got all the way down to optimizing the learning rate. From there, we ended up with a model that was 128 LSTM nodes, dropout rate of 0.2. And we had actually landed on 250 epochs as the best, but there was a bit of a gap between that and the next epoch node I had put in at 500. Full batch worked the best, which makes common sense, and the learning rate was where that is. But I did actually train it out quite a bit longer than the 250 epochs, and then right there where you see the intersection between the validation loss and the training set loss is where I actually ended up stopping the model to try and prevent overfitting. And so from this, we had the model built and trained. The root mean squared error was about 2 for both data sets. And then plotting here on the right, I have, it's delta VIX, but it's I just added it on to the previous day's close. So we predicted the delta from starting at yesterday's close and then graphed it over the actual data. And you can see it lines up pretty well. During the periods of lower volatility, it's sort of, there's some erroneous peaks. But one can imagine, it only takes probably 1 or 2 headlines to set this thing off, right? So, yeah. In conclusion, the graphs track pretty well. The erroneous spikes, they actually might be advantageous if you're looking for a more risk-averse trading strategy. It would be interesting to gather some more news sources and explore things a little deeper. And then most of the project is based on the sentiment analysis section. So if that goes poorly, the whole rest of the project would have gone poorly. And so it would be easy to try and improve by iterating through other methods of doing that. And other machine learning techniques would be probably preferred, but they're essentially another project in and of themselves.
All right. Thank you very much. So,
stop. Okay.
Yeah. Are there any questions? And I can maybe start off with one. So as a quick question, so you're training this in the last graph that you showed, that's it's the previous day's close plus the delta VIX value. When you plot the actual delta VIX versus the predicted delta VIX, do you have did you do that, or do you have an idea of how well that fits up? Because one problem that RNNs can have, so yours doesn't appear to have this, but one problem that RNNs can have, if you go back to like this data here, yeah, perfect, is that sometimes when you train them for a while, you look like you get really good results, and then you zoom in and realize that the entire graph has just been shifted to the right by 1 data point, right?
Yeah. Well, no, so I did check for that by looking at some of the more pronounced peaks. There's this pretty large one here.
Yeah.
In the middle. So yeah, I understand what you're talking about. I did check for that and make sure that the data lined up and that it wasn't just, the whole thing shifted.
Right.
But I don't know if I can, I don't think I have, I don't think I did do just the delta on its own. Because I knew what I wanted for my paper, and unfortunately, I didn't think about that.
No, that's fine. I was just curious if you happen to have it pulled up. And like I said, it didn't. Looking at your data, it doesn't look like that's what's going on. It's just that is a feature of RNNs that can happen.
Yeah. I actually in the lab had that happen to me. Well, thought I had that happen to me, but went back through and subtracted some of the things out, and it was actually the step size that was repeating itself as a seed for the song.
Mm-hmm. Nice. Any other questions? All right, well, thank you very much.
Thank you.
Okay, and next we have we're going to have a presentation on single channel speech enhancement. So Andrew, if you want to jump on.
All right, let's see. This looks like it. All right. Can you see my presentation and hear me?
Yes.
All right, perfect. All right, so my name's Andrew Stockton, and I'm going to be presenting an audio project for us using machine learning. And I hope a good takeaway is that feature engineering is a really cool part of getting better improvement in your models. So the problem I'm addressing was the cocktail party effect. And I particularly wanted to model it. So the cocktail party effect is the phenomenon of the brain's ability to focus one's auditory attention on a particular stimulus while filtering out a range of other, noises, as when a party goer can focus on a single conversation in a noisy room. It's pretty remarkable, as humans, when you're in a, whether it's like a restaurant or a bar or, some kind of crazy networking event, that you're able to like focus in on like one person's conversation amongst all the noise. And so I wanted to basically enhance speech and remove noise from audio files. So first we need to find a data set, and the two data sets I used involved one clean speech data set and one noise data set. The speech data set was from LibriSpeech, and this is about 1,000 hours of read English speech. It's various speakers of different, accents and language, like male and female. And they're reading a bunch of books. These are like audiobooks. So this was nice, a lot of clean speech. And then for noise, I found a data set from Harvard that had, I guess, a wide range of animal sounds, nature, human sounds, interior and exterior sounds. So unfortunately, there were only about 50 kind of classes here in this noise data set, but I wanted to keep it small. You can imagine that you could have like millions and millions upon hours of different audio files. So to try to keep this project in scope and not be super large, I just focused on this small noise data set. And so this is the fun part. I had to generate a new data set from these two existing data sets. So if I want to remove noise from a audio recording that has a target speaker and some background noise, I pretty much had to generate and synthesize an entire new data set by mixing the speech and the noise at various levels called SNR. And SNR stands for signal to noise ratio. So basically, I randomly sampled different, speech files and different noise files and mixed them at different levels, so that in some files the speech is louder against the noise, and then if the SNR was really low, that would mean that the noise is very loud and you can barely hear the speaker in the audio recording. So continuing this signal flow, the clean speech goes up to the top, and the noisy speech goes down on this middle branch. And for both of these signals, these are time domain signals. So you can actually window them into a bunch of little time segments and go into the frequency domain with the discrete Fourier transform. So I go into the frequency domain for both files. And on top of that, I do some other statistical tracking in the frequency domain. I calculate the energy, which you can think of as the magnitude or amplitude of different frequencies. And I also have some time domain filters that I think on the next two slides, I'll try to elaborate so that this doesn't look so mysterious to everybody. All right, so the sliding discrete Fourier transform. All of my data is in the time domain. And if you see here, I have speech and noise in blue, and then the clean speech in red, which is what I want to extract. But if you're just looking at time domain data, it's really tricky to try to figure out just by looking at like time, what's speech and what isn't. But if you go into the frequency domain, which I've put two plots here, you can kind of see like a better view of what frequency components are involved in each file. And going into the frequency domain helps the model figure out what's speech versus noise. Like speech has a very typical characteristics. And the cool thing is that this upfront signal processing is sort of modeling what's actually happening in our ears. Inside our human ears, there's actually little tiny hair cells that are actually have frequency selective characteristics. So some tiny hair cells in your ear are actually like listening into the bass in like an audio file, and some tiny hair cells are further in your inner ear, and they're listening to high frequencies. So over here, I'm just showing you the two different time signals, what they look like when you go into the frequency domain. And this is time on this axis and frequency. You can go onto Wikipedia and learn about how you can convert from time to frequency and how they're related. When I am calculating the energy down here, you can see that there's a graph here with time on the x-axis. And I have two filters, a peak tracking filter and a valley tracking filter. These are basically filters that are kind of smoothing out the noisy energy over time. And the peak filter has, what's this in my chat? Never mind. The peak filter is kind of like looking at the peak, and the valley is looking at the, the min. The valley is sort of like tracking the bottom of the noise. So let's see. So I fed all that into two different models. The first one was just a pretty small, I just had one hidden layer, and there were about 11,000 parameters. And I wanted to keep this model kind of small because I wanted to see this, hopefully maybe being embedded on like a real-time small electronic system. But I also tried using an RNN because it was time series data, but happened to be looking at it in the frequency domain point of view. And did an 80-20 split. Only looked at the frequencies that, 0 to 4,000 hertz. This basically means I was looking at audio that was about telephone quality. And I'm going to speed through because there's some cool audio tracks I want to show. But basically, the RNN performed a bit better than the DNN. I'm just going to skip to these files. So looking at this, here's an input example where I have speech and noise, time on this axis, frequency up here. I ran it through an RNN and it gave me this output. And the truth that I was trying to reach for was this target clean speech here. So you can see the RNN got pretty good compared to what the target should have looked like. And you can also see it from the time domain point of view. The RNN was able to remove noise and extract out the speech. But what really matters is when you listen to the audio, did it actually make an improvement? So to give some examples, here on this axis, signal to noise ratios, the larger the number, the better it is to hear the speech. So here I have clean speech.
I might be told that if I had wished to follow the rules of pure morality.
And I mixed in some noise, and I hope people can hear this. I'm pretty sure I clicked to share the computer audio. Let me know if you can't hear this. So here's speech mixed with noise.
I might be told that if I had wished to follow the rules of pure morality.
And then here's the RNN cleaning up the audio signal.
I might be told that if I had wished to follow the rules of pure morality.
You could try something more difficult over here, clean speech.
It is pretty clear also that the last rally of Druidism against Christianity.
And then down here, there's noisy speech with a lot of loud clapping. Oops.
It is pretty clear also that the last rally of Druidism against Christianity.
And then here is the RNN cleaning it up.
It is pretty clear also that the last rally of Druidism against Christianity.
I'll play one more and then go to the conclusions. So here's noisy speech.
A wave of despair rolled out from our Lord.
And then here's the DNN trying to clean it up.
A wave of despair rolled out from our Lord.
All right. So conclusions. We'll definitely need a way larger data set if this were to generalize to every type of sound you can find. Finding higher quality speech data would also work. The better that is, pretty much the easier it is to remove noise. there's some cool loss functions out there to explore that are more from a psychoacoustic point of view, but I didn't get around to it. There's even some more domains. You can go from the frequency domain into the Mel frequency domain. And the reason I said this was single channel is because I only use mono audio signals, but you could use stereo signals, similar to how like the human ears work. You know, we have 2 ears, and being able to exploit that spatial characteristic will definitely improve performance. And that is my presentation.
Awesome, thank you very much. So are there any questions? And maybe, so to quickly start you out, do you know how, so the RNN techniques seem to work pretty well, especially for sort of a small, or yeah, or not too much external noise. Do you know how well, or do you have any idea how well that compares to like more classical denoising mechanisms?
Yeah, I wanted to get some other recordings. I'll say that if you use classical noise reduction techniques, they use the same statistics. Like they look at energy and they try to figure out how often the energy modulates, and they're able to clean it up, but it's really hard to tune because you're tuning it by hand. And the artifacts you hear are also similar to the artifacts that this neural net also produces. I think if I were to guess, I'd say the neural net sounds better than a traditional denoising.
And then additionally, so you trained on a couple of different kinds of noise.
Yeah.
Do you have any idea like what happens? What would happen if you took a completely novel kind of additional noise and stuck it into the RNN? So
I actually tried that.
Oh, really?
Yeah, I tried Babel, so like a noise from a bar, which is the worst noise you can produce because you're telling the model like extract speech, but only extract the one person I want to talk to compared to all the other humans in the room. And it tends to just not reduce anything and just sort of turns into like a pass through. So I guess in another way to say that is that I guess it only reduces noise that it's aware of, I think is the best way to say it.
Cool. All right, well, thank you again very much.
Cool.
Okay. So next we will, we'll be looking at call probability from the Boston 311 dataset. I'll mute myself so you don't have to hear my email anymore.
Hi, can you hear me?
Yes.
Okay, great. I'll get started then. So I'm John. For my presentation, I'm going to look at using the Boston, City of Boston service request system to see if, about predicting probability of one set of category calls versus two other categories. So just some background.
John, quickly, we're getting garbled audio from you. I'm not sure if there's anything to fix it. Sorry, can you hear me really fast? think. Okay, I think we may have lost John. Sorry, just one moment. Let's see if I can. Okay, I may share whiteboard really fast. Okay, well, let's wait for we'll just wait for a minute and see if John comes back to life. This was always a danger that it was going to happen to somebody that that there were some errors. Okay. Again, John, so it looks like we can see your screen, but I can't hear you. I don't know. I'm assuming that nobody else can. Is that correct? Yeah. Okay. So it sounds like, John, it sounds like we can see your screen, but nobody can hear you. Okay, well, maybe I'll troubleshoot with John what's going on. But so maybe the thing to do at the moment anyway is to just move on to the next group. So you guys ready to present on IPO success and failure? And who do I need to make, sorry, to make somebody okay. All right. So for the group that's doing IPO success and failure prediction, I need to make one of you. Well, I suppose I can just make all of you co-hosts. Maybe that's the easiest thing to do. Okay, so you guys should be ready to present. Okay, are you guys ready to go? Okay, quick question. So can folks hear me still? Are we still alive?
Excuse me, can you hear me?
Yes, I can now.
Oh yeah, okay.
All right. So you should be able to share your screen now.
Okay, so wait a minute. So yeah, we're supposed to let Xingjian to show the screen, but so I didn't open it.
Okay, I made all of you co-hosts, so you should all be able to share your screen now.
Okay, so wait just a second.
I'm sorry, the setting has some problem.
No, it's all right. Are there, let me know if there's any troubleshooting that can be done, or that if you have any questions.
Okay.
Fabulous. All right, are you guys ready? And quickly, Mingfan, just so you know, I think you're muted right now.
Yes, okay now.
Okay.
Yeah. Okay, sorry. Sorry. Can you guys hear me?
Yes.
Yes, thank you. Can you see the PowerPoints?
Yep, we can see the PowerPoint. You guys are ready to go.
Yeah.
We're sorry, like Haojun can't see the PowerPoint. We don't know why.
No.
Oh.
Can you open?
My screen is showing the Xingjian Huang, but I can't see the.
Haojun, can you download the PowerPoint and follow along? We can tell you when we change slides. Okay, so another thing that you could try, I don't know if this will work. Theoretically, you got it? Okay, cool, okay.
So yeah, so shall we start now?
Yeah, let's get started.
Okay, so good afternoon, everyone. So today we will talk about our project, which is, like you see, the Predict IPO Success and Fueler. And I am Haojun Cao, and my teammates Mingfeng Gao and Xingjian Huang. So machine learning helps us to make our society convenience, and it can analyze the data by using its algorithm, and is widely used in many fields, such as like finance, like our topic. It's a very good chance for us to have such an experience. After learning this class, for our project, we tried 3 models to predict this issue. So first thing for machine learning is having a big data. So my teammate is Xingjian, and we are talking about this.
Okay, so after searching the internet, we can't like find a whole like data set containing all the features that we want. So we ended up like finally collecting our own data. So for from the New York Stock Exchange website, we collect a bunch of company names and search them from the Crunchbase, find their stock symbol, funding rounds, funding amount. And then on the Yahoo Finance, we found their sectors, industry, number of full-time employees, and their initial stock price and the stock price after year. And then we define their success or failure based on their stock price change. If the stock price increases, we define as success, and otherwise it's false. A failure, sorry. Then we clean the data set by deleting the company name, since it's an identity column. Also, we only keep part of the stock symbol, the exchanges, because there are several small exchanges that have only a few data. So we only keep the NASDAQ and New York Stock Exchange. Also for the industry, I think it has the same function as the sectors, but more varied. Like, so for easier for like for classification, we delete the industry column as well. And then we standardize the numerical columns by minus their means and divide their standard deviation. Also, for the stock price after year, because that column we only use for the defining IPO success or failure purposes. We cannot know like from the new stocks, so we delete that column as well. Next slide, please.
Oh, sorry.
So now the graph shows the division of the labels. After cleaning, we still have over 900 data. So we have 417 success and 518 failures. And from the two exchanges, we can see we have more NASDAQs than the New York Stock Exchanges. And for the sectors, there are totally 12 sectors, and mainly they're from healthcare and technology. For preparing the models, we dummy coding the categorical features for easier to calculate the correlations and the distances. And then we splitting the whole data set into 80% training data and 20% testing data. So now we are going to talk about our 3 models in the following order: the categorical linear models, decision tree, and hierarchical clustering. Now Haojun is going to talk about the linear models.
Yeah, so like we see, the first model of our project is categorical linear regression, and it has so the first one is the logistic regression, and like as the 2 tables showing here, we tried all features to train the model. The accuracies for training data and testing data were about 0.602 and 0.524, which after we tried different combinations of features, we found if we take out sector and initial stock price, these 2 features that were less correlated to the model, we got accuracies for training data and testing data were about 0.575 and 54.5. And for the next one, the linear discriminant analysis, as we shown here, so the training data for all features is 0.599, and the testing data for it is 0.535. Sorry about that. And for we try the same features, like take out the sector and the initial stock price, we got 0.572 for training data and 0.545 for testing data. And for the last one, the quadratic discriminant analysis. So similarly, so we got the training data for all features is 0.571, and for testing data is 5.503. And the same way for the 2 features, we took out sector and initial price is 0.57 and 0.535 and 535. And after we do all the table, we can find the testing increase. We can find the testing score increase slightly, and the training score decrease slightly. And we will talk about on the conclusion part, and we also find another difference is after taking out 2 features, the models are getting high accuracy on predicting F and low accuracy on predicting S. That's what we got for the categorical linear regression. And for more models like this decision tree, my teammate Xingjian will talk more about it.
So we used a package from sklearn, and we tried the depths 2, 3, 4, 6, and 4, and got the following accuracy scores. So after looking at the scores, we find the depths 2 has the highest testing score, and even though we increase the depths, the training scores goes up, but the testing score goes down. So we think depth 2 is the optimal choice. So on the left, that's the decision tree graph we got. Also, we found there are a couple of features that are more important to the models, which are employees, funding rounds, funding amount, and initial stock price. It's also interesting to find like there are only three categories in the sector column that are a little bit correlated to the 2-depth model. So as a result, we got 0.624 as the training score and 0.524 as the testing score. Similarly, at the linear models, decision tree model also can predict the failure more accurately than the success. Now, Mingfeng is going to talk about the hierarchical clustering.
After using two classification methods, we tried to use clustering to see the feature similarity. Here, we choose the agglomerative hierarchical clustering with two clusters. First, we use SAPA package to generate a linkage matrix, which stores all the distances generated from singleton clusters to family a single cluster containing all data points. Here we used a word method to compute the distance between two clusters. In this case, in SAPA package, if we choose word methods, and then the Euclidean distance is our only option to be used to compute the distance of two data points. So here we choose the combination of word and Euclidean. After this, we still could use SAPA package to visualize this linkage matrix, such as the full dendrogram. This one is the graph of the full dendrogram. Yeah. This one is the last step of agglomerating the clusters. It's part of the full dendrogram. Yeah. Yes. And because this is the last step of the full dendrogram, so here one clusters contain 395 data points, and one contains 540 data points. We could, yes, this is the two clusters. What we expected, but this is just a graph. In order to assign the cluster label to each data point, we use sklearn package to peruse the full dendrogram to the second graph we get previously. This function can peruse the full dendrogram to have only two clusters and then predict the cluster label for each data point. Because we already have the IPO label for each data point, so we can compare these two labels of each for each data point, and then we can get the model accuracy. We also tried all possible combinations of features to see the accuracy. As a result, the combination of employees and funding rounds gives the highest accuracy. Here, the accuracy using all features is 52%, but the accuracy can get 56.3% if we just use two features. And from the confusion two confusion matrices, since we can see if when the accuracy is higher, we can catch f, we can catch data point with f IPO correctly. Yeah. That's our modeling part. But after the analysis of three types of models, we can conclude that how many full-time employees a company has, that is the employee feature, and the number of funding rounds and the number of $1 million of the corresponding funding amounts. These three features are more relevant to the IPO success rate. The other features don't influence the success of IPO much in our models. However, our model testing accuracy is not ideally high. We think there are several reasons for it. The first one is IPO success or failure. We defined was based on the stock price differences. That is the difference between the initial stock price and the stock price after 1 year. So models without the stock price after 1 year may have low accuracy. Second one is our data size is about 1,000. So it's not big enough to support our analysis. It also may lead to inaccurate analysis. I think this maybe there are some other factors influence our models, but I think if we have enough sets of data, I think we can get more accurate analysis and provide more valuable information. Yeah, that's it. Thank you all.
Thank you.
Thank you very much. So are there quick questions? And I will start you off with one. So I know that so again, I'm going to use some pre-knowledge. I know that one of the issues that you guys had here was just getting data, since so much financial data is incredibly locked down, and no one's trying to give it away for free. But if you could have added some features to this data set that you think would increase your accuracy, what additional features would you find?
Sorry, what?
Yeah, sorry. What features do you wish you could have had in this data set that you weren't able to get?
Yeah. I think the year these companies were founded or wanted to the public, I think they should have an effect on the IPO.
She means the publication year of the stock.
Yeah.
Uh-huh. And then do you guys see Jin's question there?
Mostly we get advice from professor, yeah, the features.
Yeah, so with the I mean, you guys, you did the full accuracy, or did the accuracy analysis for the decision tree features as well. So I'm trying to remember, were there oh yeah, sorry, that was the other question I had. So it seems sort of strange that that the linear models are continuously predicting, when you do the linear models on two variables, that they're predicting that everything's false all the time. Right. So do you have any idea, like, what those 7 things that they're predicting, that they're predicting failure, do you have any idea what those 7 data points that they're predicting as successes are, or what's the difference between those and the several hundred data points that are being predicted as failures?
Oh, we didn't look. Sorry.
It's a very left field question. Don't worry about it. Okay.
Yeah, but it's interesting. Yeah. Yeah.
All right. Well, thank you guys very much.
Thank you.
Thank you.
And John is back. So, John, if you're give another go. Sorry, I'm making co-host real fast. And then so you should be able to share your screen out.
Can you hear me?
Yes.
Okay. I think I'm having internet connection issues here. We're in the middle of the storm. So can I put my phone number on the chat? And if it cuts out again, could somebody text me? Because last time I just went till the end. And
oh no. Yeah, absolutely. I'll text you if you get cut out.
Thank you. I'm not sure if it's internet or Zoom, but I'll try again.
Yeah.
And can you see my screen?
Yes.
Okay, thank you. So my name's John, and for this project, I look into the 311 data set from the city of Boston, and to see if I could predict the probability of one service type request based on other service type requests in the same data set. Can you still hear me?
Yep.
Okay, great. So just to review, the 311 service is the City of Boston's system for requesting non-emergency city services or information. These can be made through dialing 311. There is a BOSS 311 public app. There's a city worker app. You can make a constituent call or a visit to the mayor's office, and there is a mobile city services truck. You can make requests that as well. So here's some screenshots of the BOSS 311 app, and as you can see, you can select a service type from a list available, and then when you make a request, it collects your location information, which was key for this project. So I wanted to look at the notion of co-occurrence between different service call categories to determine if taking two, specifically to see if two service call categories, the probability of getting two in one location could predict the probability of a third. So I did this through the data set available from the City of Boston's Analyze Boston Open Data Set Hub. So I collected the 2019 311 set of service requests. They was a little over 259,000 The data had 28 features. There were 44 different service categories and 24 neighborhood categories. So my initial data analysis, it was mostly categorical data, except for the latitude and longitude. So I first encoded everything with category codes and then ran a heat map. I didn't get a ton of correlation, except some highly correlated between the fire and police districts. So I dropped that information. I then, sorry, did I go back here? So I looked at the latitude and longitude information, plotting them, saw that it looked Gaussian in nature. So decided to look to see if to fit a model to that, because this would be a categorization problem. So I was referred to look at the Gaussian mixture model, which could could be used to fit multi-dimensional distributions. So we went over this briefly in class, but I'll review that it's an unsupervised learning algorithm. It's similar to k-means, but in that you can specify a number of clusters. They also, in the code, they call them components. So if I use components, I'm referring to clusters as well, but that you want as a hyperparameter. It differs is that you fit around a Gaussian density with a covariance. That's one feature of the data that you're giving in. And it assumes it comes from a mixture of Gaussian distributions. And then with each data point, the GMM learns the probability that it belongs to a cluster. And it's not a hard clustering. I believe that's the term, the terminology used. So points can belong to more than one cluster. And whereas k-means, you were using a circular clustering, this allows for a non-circular form, which ellipses, which I'll demonstrate in a bit. So this is implemented in scikit. You can create a GMM model with passing in the number of components or clusters, as well as the covariance type, which that would determine the shape of your cluster fit. And then you can then fit that GMM model to an array of data points. And there is a score method built in, which returns the log likelihood of the model, the probability that the observed data would be in the GMM. So here is just a plot of the latitude and longitude. First on the left, it's all the service calls from 2019 for the health department category. And to the right is the number of the points from the needle program category. So I then passed in these set of latitude longitude pairs to my created GMM model and then fit to get the following information. So this particular one was passed in with 5 components or clusters. So it creates labels on the data, which correspond to the different colors and points that you're seeing there on the screen for the computed distribution pair, combined distributions. And so here's a model with 30 components, and you can see there's the more different colors, and it doesn't show the overlap as well with this particular coloring scheme. So you can also put ellipses demonstrating the distributions over the data, such as this. So you can see this one is the GMM with 5 clusters, and you can see there's there's some overlap there. And here is the one with 30 clusters. So as far as getting the probability of a third set of points fitting in this distribution, there's a predict proba method built into the GMM class. So you can add a new array as a parameter, and it looks at the probability of each Gaussian cluster in your GMM for each sample in the new array. So for example, if you had a GMM with 5 clusters or components, and you would then pass in a new data set of 5,000 data points, it would return a 5,000 by 5 array. And so each entry, each column would be the probability of finding each point in one of the 5 clusters. So you get in the first row the probability of 0.1 in cluster 1, 0.1 in cluster 2, 0.1 in cluster 3, up to cluster 5. So that's how I went about trying to find the probability of the third data point in this in my created model. Oops, sorry. It's a little lag with going through my slides for some reason. So here on the left is the, sorry, the labels appear to get cut off on the graphs, but the left is, so I had 5, it's the 5 cluster model, and I passed in a new set of data points for the graffiti service calls. And this, so I took for each data point, I selected the cluster that it got the highest probability of being in from the previous function I just showed, and then totaled those up. And so on the left, the highest probability was in the 4th cluster. And then on the right, I have the 30 cluster GMM with that graffiti service call data points information passed in. And in this case, I got the first component of the model had the most had got the most hits for the highest probability. As far as next steps, I wasn't completely convinced that this predict probability method was the best way of going about this. So I wanted to further investigate that. I was also trying to see if I could get the optimum number of data points from the sort of a best set of the 3 for 3 categories based on probability. I wanted to look into that further. And then as far as, so the log likelihood I found, and I did a test train validation split, and in all my series, the log likelihood or score for the on each one increased as I added more components. So the 30 component GMM got higher scores than the lower ones. So I was interested in finding an optimal number of components to find for a model if when adding too many would be would decrease. I couldn't find that in my data, but so there's a feature of the GMM class in Python, the Bayesian information criteria, which I found an article which said could be used to find an optimal number of components. So I was considering looking into that further. So that's what I got. Are there any questions?
Thank you very much. So are there any questions? If so, please please type them in. And that's just a quick getting started. So it seems like with this there's a possibility of basically just clustering by population centers, right? That that instead of looking at conditional probabilities in some sense, you're just sort of looking at like where do most people live? How can you think of a way that you could, or how in a future iteration of this, like how maybe would you account for that?
Well, for example, like just looking at the map and then at the when just plotting the longitude and latitude, I don't know, like the Mass Pike connecting Greater Boston with Austin Brighton. There's no service calls from there, so it would be maybe. As far as sort of, I don't know if you look at it like just white space on the graph or sort of trying to, overlaying major roadways because it's sort of pulling one layer off the graph, off the map that way. That's what I initially thought.
Well, thank you very much. And thank you to everyone who presented today. And looking forward to the presentations tomorrow. Yeah, and thank you for everyone for doing this in the non-standard format. And I think it went pretty smoothly all in all. So yeah, I will send out the link to this once it gets reprocessed and whatnot, and you can take a look and see if you want it uploaded. And yeah, I look forward to seeing seeing the presentations tomorrow. And don't forget that tomorrow there are 2 sessions. One is at 2 p.m. And that's going to be the segmentation group. If you want to stop in and see them, one of the group members is out of the country, so they want to shoot a little bit earlier. All right, have a fabulous evening. Unless there are any questions or comments or anything else. Great. All right. Well, thank you all very much. Have a great night.